Okay, now we're going to take a look at rotational symmetry. We're going to start off by looking at a regular hexagon. And first thing I want to point out is that I'm in edit mode here in my Google Slides and not in presentation mode. The reason why is when you're editing, you can rotate an object, and when you're in presentation mode, you can't do that. So you're going to see all the information here on the screen at once, but I'm going to kind of go through it just like it was a presentation. So the first thing that I'm going to want to do is say, what is the smallest amount of rotation that will make this object look exactly the same? So as I'm rotating this object, if I were to rotate it like 20 degrees, it doesn't look like it's right on top of the other image. In other words, I can still see the figure behind it. As I rotate it more, and if I rotate it a total of 60 degrees, then it's right on top of itself, just like it was when we started. And I can do that again by rotating it another 60 degrees, and I can do that again by another 60, and so on. So one thing I want you to note is as I'm going around here, I'm going around 6 times. Another way of figuring this out, other than actually rotating it and figuring out how many degrees you're turning it, is by looking at the fact that it's a regular figure. Any regular figure means that the lengths of the sides are the same and all the measures of the angles are the same. Whenever you have a regular figure, all you need to do is take 360 degrees, because that's how long it takes you to go all the way around, and then divide it by the number of sides. So in this case, that's 60. But that's only true if it's a regular figure. If it's not a regular figure, in other words, if all the sides aren't the same length and the angle's the same measure, then that does not work. If we take a look at a kite is defined as a quadrilateral with 2 pairs of congruent equal sides. Now, in this kite, this is not a regular figure because all the sides are not the same length and all the angles are not the same measure. So as I rotate this one around, you'll notice that there's no place I can stop so that it's exactly on top of itself as I'm rotating it around. There's no place that I can stop and do that until you get back up to 360 degrees. Now, when it's 360 degrees, that's really nothing special. Everything has 360 degrees of rotational symmetry. So instead of saying that everything has 360 degrees, we just say that if that's the only rotational symmetry, that it does not have rotational symmetry. So if you have to go 360 degrees to go all the way around to get it to land on top of itself, then we say it does not have rotational symmetry. Let's look at the rectangle now. When I turn the rectangle, if you watch the number of degrees, in order to get on top of itself, it'll be 180 degrees. Now, if I were to continue that and come up here, it's also 180 degrees. Now, again, this is not a regular figure because all the sides are not the same length, but it still does have some rotational symmetry. And then the next one we're going to look at is a very special one, the circle. In a circle, if you're rotating it around a circle, it does not matter how much rotation you have. You could have a very little, you could have a very lot. It will always end up right back on top of itself. So we say a circle will have any amount of rotational symmetry. Now, there are several other figures in this presentation that you can try to figure out if they have rotational symmetry or not. So what you're going to want to do is I'm going to have a link to this presentation. If you make a copy of this link, then you can go ahead and in the mode of edit, you can see how many degrees of rotation it will take to make something land on top of itself again. So that is rotational symmetry. I hope that was helpful.